Previously, we covered the core foundations. Now in part 5, we tackle solar flares. Explained, what actually happens. When the sun erupts, part 5, protecting our technology, how we shield against solar storms. Orbital dispatch script. In the last episode, we explored how scientists forecast solar weather using spacecraft monitoring and magnetic field models. But predicting a solar storm is only half the battle. When a major geomagnetic storm hits Earth, billions of pounds worth of technology hangs in the balance. So how do we actually protect our satellites, power grids, and communication networks from the sun's fury? The answer lies in a combination of clever engineering, automated systems, and sometimes old-fashioned human judgment. Today, we're examining the ingenious ways we shield our technology from solar storms. Satellite protection, safe mode, and shielding. Let's start with satellites, our most vulnerable assets. When space weather forecasters issue a geomagnetic storm warning, satellite operators don't just cross their fingers and hope for the best. They have specific protocols. First, they can put satellites into safe mode, essentially parking them temporarily. Non-essential systems shut down. Solar panels turn edge-on to reduce surface area, and the satellite stops performing complex maneuvers. Think of it like a ship battening down the hatches before a storm. For hardware protection, engineers use radiation-hardened electronics. These components cost significantly more than standard electronics, but they're designed to keep functioning when bombarded by high-energy particles. Critical systems also have redundant backups and error-correcting memory that can fix data corruption in real time. Power grid defense, the human element. On the ground, power grids face a different challenge. Geomagnetic storms induce currents in long transmission lines, potentially damaging expensive transformers. The defense here often comes down to human operators making difficult decisions. When a severe storm warning arrives, grid operators can temporarily reduce power loads, disconnect vulnerable transformers, or even implement controlled blackouts in extreme cases. It's a balancing act between protecting equipment and keeping the lights on. Some utilities have installed special monitoring equipment that measures geomagnetically induced currents in real time. If readings exceed safe thresholds, automated systems can trip circuit breakers faster than any human operator could react. Aviation and astronaut safety. Airlines face unique challenges during solar particle events. Polar flight routes expose passengers and crew to higher radiation levels, so when forecasters predict a major solar proton event, airlines reroute flights to lower latitudes. These diversions cost fuel and time, but they're essential for safety. Astronauts have perhaps the most direct protection protocols. The International Space Station has designated shelter areas with extra shielding. When space weather alerts reach certain thresholds, crew members must immediately move to these protected zones and remain there until the radiation levels drop. Communication networks, redundancy and adaptation. Communication systems rely heavily on backup plans. GPS satellites, for instance, have multiple atomic clocks aboard. If radiation disrupts one clock, others maintain accurate timing. Ground-based systems automatically switch to alternative signal paths when satellite communications become unreliable. Military and emergency services maintain HF radio systems, specifically because these frequencies can still function during severe geomagnetic storms, even when satellite communications fail entirely. The bigger picture. What's remarkable about our solar storm defenses is that they largely work. The 1859 Carrington event would likely cause far more disruption today, given our technological dependence. But we're not helpless. We've built resilience into our most critical systems, and we're constantly improving our protective measures. The key insight is that protection isn't about making technology completely immune to space weather. That would be prohibitively expensive. Instead, it's about building smart systems that can recognize threats and respond appropriately, whether that means shutting down temporarily, switching to backup systems, or simply riding out the storm with hardened components. These protective measures represent decades of learning from past events, studying the physics of space weather, and engineering solutions that balance cost with reliability. Next episode, Part 6 explores the next key question. If you're enjoying this series on solar flares and space weather, subscribe for more clear explanations of how our universe works. That is Part 5 of Solar Flares Explained, what actually happens when the sun erupts. In Part 6, we explore the next key question. Subscribe so you do not miss it.